We live in a built world. Engineering and technology built upon innovations and inventions, stretching back thousands of years. Some of our creations, like machines, boost our body's abilities. Others help us reach outside our comfort zones. We have left an indelible mark on the planet. And now the time has come to use our skills to make a better world. Like turbocharging the ancient sling.
The idea is 50,000 years old.
To launch satellites in a way we've never done before. A device that boosts our sense of touch. To share a dance.
I felt I was moving along with you. Begin.
Or aid in movement. A machine to boost a human experience and inspire a new generation.
Oh my gosh, so good.
Or even recreating a sense.
Good to go.
To replace something that was lost.
That was the first time in years that I had a sensation, a vision.
Building stuff. Boost it. Right now on Nova.
As an American-based supplier to the construction industry, Carlisle is committed to developing a diverse workplace that supports our employees' advancement into the next generation of leaders, from the manufacturing floor to the front office. Learn more at carlisle.com.
Earth is home to more than 8 billion people, living in a world full of human invention.
Certainly in our modern world, we don't really appreciate how saturated with engineering it is. Every pen you pick up to write something with has been engineered. The paper on which you write has been engineered.
Humans are engineers at heart. You see a problem and then you identify a solution. And we've been doing that forever.
This thing we call engineering, what is it? Where does this impulse to make things come from? Anthropologists tell us that the roots of invention reach deeper into our past than we ever imagined. According to our best records, some 3.3 million years ago, our ancestors figured out how to sharpen a certain kind of rock, creating a tool for cutting much better than our teeth, boosting the chances for survival.
Humans dating way, way back in time have been inventing things that help efficiency, that help their survival, that help drive them forward based on the needs of that time.
It's an innate desire to make things better through making tools.
And ever since, one idea has led to another. And every invention around us today can be traced back to those first tools.
We have a cutoff at T-minus 30 seconds.
Since the 1950s, rockets have been our go-to workhorse for sending people and payloads into orbit. They are some of the most complex machines ever built, the ultimate boost into the sky. But they aren't exactly new. Even modern rockets have historic roots, going back in time. Some ancient projectiles were powered by chemical explosives like gunpowder. In 1232, Chinese soldiers repelled a Mongol army using flaming arrows, likely propelled by simple rockets. Today, rockets are far more powerful, able to send humans to the moon and the International Space Station.
Solid rocket ignition.
But rockets have limitations.
Putting things in orbit is hard. It takes a lot of energy. Rockets are hard. They take a lot of energy.
Basically, the amount of fuel required for rockets to reach, the outer reach of our atmosphere is the limiting factor.
Something like 92, 93% of the mass of any rocket is fuel, leaving about 5 or 6% for the actual structure and only 2% for the payload.
There is a high demand to put things into space, but there are limited means of getting it there.
But that may soon change. If engineers at a company called SpinLaunch can make the dream imagined in this promotional video a reality.
SpinLaunch is a highly unique way to get to space. The idea itself goes back to caveman times. It's a sling.
A sling is an ancient hunter's weapon. It's an improvement on the arm and shoulder's ability to throw a stone. Archaeologists have found ancient evidence of slings, some at least 12,000 years old. For Jonathan Yaney, the sling is an inspiration.
It rotates, and at the end of a rotational element, you have really, really high speed.
So Jonathan embraced a radical idea. Use that speed to launch a spacecraft into orbit.
A sling is something you spin around, and basically the more you can spin it, the more force you can basically put on the release of whatever you're slinging out. But if you scale this up, that same principle has the ability to launch a rocket into orbit. That's incredible.
That idea has been met with skepticism, so the SpinLaunch team has much to prove.
It is one of those ideas that just sounds too crazy. I think it's good to look at things from a place of skepticism at the outset, but then you have to be objective about looking at, well, what are the underlying physics and what might really be possible?
The SpinLaunch team is using electricity to generate rotational speed faster than the speed of sound. The proposed payload, a satellite encased in a bullet-shaped shell, must withstand up to 10,000 Gs, or 10,000 times the force of Earth's gravity, until it is released at just the right moment. Once the aeroshell gets around 40 miles up, the casing would separate to allow two small rocket engines to propel the payload the rest of the way to low Earth orbit.
The arm itself that's actually spinning around needs to be able to withstand it to a certain degree as well. So you have a need to not only make sure that it's structurally sound, but there needs to be precision in the timing and the programming of that actual release point.
I don't have any classical training as an engineer. I self-educate. I read a lot of books, lots of books, and then I read them again because I didn't really understand them the first time. I became an engineer along the way.
The team's first goal was to build a proof-of-concept mass accelerator at 1/8 scale, to validate the key technologies and use it as a testbed to spin potential space-bound components at many times the force of Earth's gravity.
Also known as G-forces, and G represents 1 unit of Earth gravity. When a pilot pulls up on the yoke of their jet and they make a hard turn, they'll feel the equivalent of multiple times Earth gravity, upwards of 8 Gs, for example.
But SpinLaunch payloads will have to withstand forces orders of magnitude stronger, as many as 10,000 Gs. So the team is working on building and testing components that can survive such extreme acceleration.
You know, in some ways, we humans are sort of timid. We feel most comfortable with things that look like things we're used to. So you can't really tell at the outset whether that thing that you're going that's outlandish is really gonna work.
Today, the SpinLaunch team is asking a critical question. Can a payload like a CubeSat survive 10,000 Gs?
So a CubeSat is this miniaturization of satellites, literally making them into these little cube components. So this 10 centimeter by 10 centimeter by 10 centimeter unit is one piece that can be added on top of each other like Lego blocks. So we have some of the most critical subsystems that you would see on any satellite. We have a solar cell here. It generates a current that charges this battery up, and then the battery stores that energy, right, and distributes it to all of the critical subsystems that require electricity. So the OBC, or the onboard computer, is one of them. This is the brains of the satellite.
The team is confident the CubeSat as a whole will survive. But so far, they've only tested individual components and never the whole system.
You know, it's a very, very common strategy in engineering to say, we're going to break this problem into small parts. We're going to solve each of the original parts, and then we're going to put it back together again.
The team aims to test some of the components that are typically found on CubeSats, starting with the computer.
So this is saying, effectively, its power rails are all working correctly. It looks to be talking to the world just fine.
So far, they know that the battery pack is particularly vulnerable. A pre-test of the battery pack system didn't make it out of the accelerator in one piece.
This gave us a great benchmark. When it hit 7,650 Gs, that it was pretty darn close. And we didn't have to do all that much to make it compatible with our launch environment. The batteries aren't designed for 10,000 Gs natively.
The SpinLaunch engineering team had to figure out how to make the batteries more resistant to the high G-forces.
So this is the original.
We saw these batteries laying on top of each other. The concern there is that when you're on the bottom of the stack, you're getting 3 batteries worth of mass squished onto plus your own mass.
Yep.
This orientation of the battery cells didn't work out so well in the spinner.
The G-forces are going this way, and you can even see the bolts are embedded and bent into the base here.
One of the things that we did was turn it sideways.
Yep.
Right? Let each battery support itself and itself only. So we're going to fully populate this satellite with all of the key subsystems that we're testing out here. This is the pre-spin test of the solar cell, 1.2 volts. And then after we're done with the test, we will check it out again and make sure that it's still getting a similar voltage reading. This is going to be the first time that this unit, with everything in it, the battery pack, the computer, is spinning up to 10,000 Gs.
Reaching the acceleration required for launch is itself a difficult engineering problem.
There we go.
At those speeds, friction just from the air would be intense. So, the inside of the accelerator is actually a giant vacuum chamber.
If you can pull all of the air out of it, then there's no more air resistance and consequently heat on the rotational structure.
There we go. Now we're going to go let the vacuum chamber draw down the pressure, and then we can spin up.
Accelerating system. $9,000, Mach 1.1, 95, 96, 97, 98. 10,000 Gs coming down. Time.
How long, Daisy?
Go. Well, look at that. I don't hear any rattles. Looks like it's intact.
The pressure one feels when you're hoping for success is mostly about the incredible personal human investment that's gone in, and not wanting to let down all of your colleagues when the moment of truth comes.
Let's crack it open. I'm going to test voltage on the solar cell. Yeah, so 0.8, that's in a reasonable range. Okay, so now we will take out the computer. Looks like it is intact.
It's still responding when we send it messages, so it looks pretty good.
I would say that that was a successful test. Pretty cool. Woo!
SpinLaunch has done what engineers do. Methodically design, test, evaluate, and repeat as they step their way up to a system big enough to send payloads into low Earth orbit.
We went to the desert of New Mexico to build a flight test system. at a large scale that would allow us to essentially prove that we had not only the technology validated, we could test our own ability to construct and to execute on a system of this magnitude and scale.
Launching at 1/3 scale was a powerful milestone, spinning the payload to more than 1,000 miles per hour.
It was an emotional moment for the team. You have to have a little bit of faith to bring something like this to that level and to that scale. We've conducted 10 successful back-to-back flight tests. We haven't had a single failure, and I think that's a testament to the practicality of the technology.
This will be for the first time since we've gone to space as a species that we'll be doing it differently.
It's common for engineers to build on an old technology, transforming it with new materials to scale their way to innovation.
It's with a spinning arm that's throwing satellites into space. That's totally new. How could that not be exciting?
When you look at cutting-edge technologies today, you can see that it's just being built upon the things that we've already seen from the past.
Sometimes we boost technology from the more recent past. Consider something we take for granted in everything from cell phones to cars to video games. It's called haptics, vibrations and other physical sensations that enable our technology to talk back to us through our sense of touch. At Harvard, scientist and engineer Shreya Srinivasan is thinking about those physical feedback loops every time she performs an ancient dance.
I've been dancing since I was very young. The ideas around movement and sensory feedback have been percolating in my brain for a long time. When I dance, of course, I'm intimately aware of my body and its movements. What the audience feels, however, may be limited by their conditioning or what they can perceive visually. I am a biomedical engineer by training, and at some point I started to wonder, can we use the receptors in our skin to communicate the complexity of the rhythms that are embedded within the choreography? And would that enable the audience to experience then the dance to a higher dimension?
Shreya turned her curiosity into an engineering problem. Could she share the rhythmic complexity of the choreography as she feels it in her body with the audience? To find out, she and her dance company co-founder, Joshua George, are conducting trials at Harvard's motion capture lab.
So we're gonna grab this metatarsal point.
The motion capture system reads and records the position of the dots placed on Joshua in order to create a digital version of his movements and understand the biomechanics of the dance.
Great. But more importantly, we're interested in capturing what's not readily visible to the eye. So muscle activation, for example, or forces to the ground.
Now can you flex your biceps?
Audience members can see the movements, but they can't feel the force of a step or a jump.
If you think about how humans interact, we like shaking hands, we like hugging. So being able to tap into that sense of touch, or as it's sometimes called, embodiment, is a gateway into allowing you to be and experience something that you're not immediately doing. For example, it'd be great to feel how a dancer moves.
So as you flex the bicep, you can see in yellow the activation of that muscle.
We have these reflective markers that we put on someone. We have them do a certain movement. We take that information, kind of convert that into body movement, quantitative data.
What we think of as haptics embedded in technology has roots in aviation. As planes advanced, pilots no longer felt mechanical vibrations in the controls when the plane was about to stall. So haptics were used to replace these vibrations artificially, preserving the warning.
Haptics is super critical, very innovative in the design process because it has the ability to really blend the physical world with the digital world.
In our analog world, haptics were everywhere. Things felt. You pushed a button on your radio and the button went clink and you could feel it. My brain is evolved to sense whether that action that I've taken with my finger has resulted in an effect.
Shreya's team is applying this concept to dance.
Take a feel and see what you think.
And the team is using modern technology to develop it.
At the moment, we're using 2 different types of haptics on the phone. So we can set them at different intensities, different sharpness. We can also vary how long they are. We're able to then assign a haptic pattern or a vibration pattern to that move and have it happen at that time during the song or during the performance.
They're under pressure to work out the kinks. They're giving a performance the next day, and they hope to work with the audience to test the system.
Okay, yeah, I think we're set for Friday.
Besides enhanced dance performances, Shreya's lab is also using haptics to do research to help medical patients with muscle spasticity move more smoothly. They're asking if vibration feedback can reduce the symptoms of spasticity, a condition that causes muscles to stiffen, making them difficult to move, often as a result of spinal cord injury or traumatic brain injury, ALS, multiple sclerosis, or cerebral palsy. Patrick Paraso, a PhD candidate, is one of Shreya's students.
With spasticity, it feels like someone is holding your limb in place. Anytime you want to move, you have to struggle against yourself.
In the motion capture lab, Shreya is working on a potential solution.
The nervous system is kind of like an orchestra, and conducting it is the brain, sending signals but also receiving feedback about which parts are playing what. And having them work together is the key to executing movement and moving seamlessly in the world.
In typical arm motion, the bicep contracts to bend the arm at the elbow, while the tricep relaxes, and the tricep contracts to straighten the arm, while the bicep relaxes. The device that they're building is designed to pick up activation of one muscle and then mechanically tell the opposite muscle to relax.
In a patient with spasticity, for example, there's co-contraction. So as your bicep contracts, your tricep is also contracting, and that causes that movement to be rigid.
So we're targeting the biceps and triceps. Let me know if it's too tight.
Biomedical engineering requires a fundamental understanding not only of the basic engineering principles like mechanics, electronics, and computer science, but also of the fundamental properties of the biology of the human body.
Step 1, put the prototype system on student volunteer Annie and use it to collect data with a simple reflex test.
We've attached EMG sensors. So EMG is electromyography. We're going to record the activation of her muscles and then display it on this laptop.
Yeah, I think that works. Oh, yeah.
Yeah, that was a stronger.
Step 2, measure the amount of muscle activation when the device vibrates to see if the activation goes down.
So now we're going to turn on the vibration.
Here, what we're looking at is, can we apply vibratory stimuli at just the right time, at the right amount, and the right parameters to relax the relevant muscles to allow for more free movement?
Yeah. All right, so now it should be stimulating on the bicep. Can you feel it on your bicep?
Yes.
Yep, right there. All right, great.
The next step, preliminary analysis of the motions. The hope is that vibration reduces unwanted muscle activation, so they can use vibrations in their device to relax the targeted muscles. If they can demonstrate that, then eventually they plan to build a device that will detect activation in one muscle and determine which other muscle to deactivate.
Begin.
Boosting flexibility
2
and restoring motion. In today's test, the device is giving them encouraging data, confirming vibration as an effective strategy for relaxing specific muscles brings them one step closer to developing a therapeutic device for spasticity.
The feeling that we were able to, what appears to be successfully, relax those muscles with vibration was a very good feeling because it means that we're one step closer to help people with spasticity move more easily.
from one test to another.
Good evening, everybody. Welcome to Decoded Rhythms. The human nervous system
The first opportunity for Shreya and her dance company to add a layer to the performance through haptic feedback.
Sensation is the gateway to the human experience.
Audience members download an app, and as they watch and listen, they'll feel synchronized vibrations.
We're hoping that the audience can be more in tune with the performance by giving them this sort of understanding haptically what the dancers are doing.
I thought it was a good work in progress demo. Most of the technology aspects worked well, everything synced, and it was exciting to just see people's initial reactions to it.
I love this. I'm an ex-ballet dancer. There's something about having this motion and movement in my hand, but I felt I was moving along with you, and that was really cool.
Combining two worlds, each adding a bit to the other.
I would say that the data that we're gathering from the dance work, the biomechanics, the ability to classify movements, to interpret intent, all of those higher level insights will guide us in the development of patterns for patients with spasticity.
3, 4, 5. Relax.
We all have physical limits, but tools of all kinds help us go beyond what our bodies can do on their own. Simple machines like levers and pulleys and screws boost our strength. But we also make tools just for fun. Every invention starts with an idea.
We're trying to see how much play there is.
For Tahira Reed-Smith, her idea comes from a childhood passion. Double Dutch.
Growing up in Bronx, New York in the 1980s, double Dutch was just what you did as a little girl.
This double-rope version of jump rope was brought to New York by Dutch settlers in the 17th century. More recently, it became popular, particularly among black girls, in cities across the U.S. There are even fiercely competitive national competitions, and in some high schools, it's recognized as a varsity sport. To play, double Dutch requires 2 people spinning ropes in opposite directions, and at least 1 person to jump. Tahira dreamed of a machine that would allow her, an only child at the time, to play double Dutch whenever she wanted. In 3rd grade, she won a contest for that concept, and in the years that followed, she never gave up on that dream.
Major passion project. Talking about an idea that I've had for decades.
Today, she's a mechanical engineer and professor, working in human-machine systems. And she's building to her ultimate dream, to create an affordable version of her invention that people everywhere could enjoy. Meanwhile, another engineer, Sky Leilani, is working on her own double Dutch prototype. Sky works at a robotic software company.
When I was in college, I found Dr. Reed's double Dutch machine at a point where I was feeling like I couldn't get where I wanted to go. I was just surrounded by a lot of people who didn't look like me. I saw she was from the Bronx, which is kind of similar to where I'm from, and that really inspired me.
Problems that matter, that are informed by culture, that are informed by background, can stimulate the desire to get into engineering, the desire to go about this process of creating something that didn't previously exist. The problems which we decide are important enough to solve are influenced by someone's background and someone's culture.
Tahira has come to Viam Robotics in New York City to collaborate with Sky, bringing along her goddaughter, Sanai, part of the latest generation interested in engineering double Dutch.
When I first learned about Sky, it really touched me deeply because I didn't know that people were watching me from afar.
When I was looking at your designs, I was just like, wow.
I was just very encouraged by it, and I was also impressed by her passion and her excitement.
Skye isn't a mechanical engineer like Tahira is. She's iterated on Tahira's design, adding computer-controlled motors and a software interface to control the two ropes.
What are the traits of an engineer? I think it's hard to generalize. I feel like there's many different kinds of engineering. There's many different kinds of skills required in the different types of engineering.
She's modernized it, writing code to control it. There's vision for even an app, and doing everything largely through computer software and electronics. Very little mechanical engineering.
As Skye describes her approach, Tahira sees that Skye is running into a familiar problem: synchronizing the ropes. The ropes need to extend in a high arc, turning in opposite directions and staying 180 degrees out of phase with each other. In other words, when one rope is on the ground, the other should be directly overhead. As they rotate, they need to maintain a regular rhythm to truly create double Dutch. It looks easy when a person does it, but as Tahira and Skye know firsthand, it's anything but simple to engineer.
That was wrong. The motor is always the most challenging aspect, and that is how it was with us. With double Dutch, the biomechanics that people use to get it to, it looks so seamless.
Yeah.
But trying to recreate that in a robot,
yes,
you realize.
We have to ask ourselves, how does the biology do it with materials and information processing units that no engineer would dream of using? How is it that we can move both ropes so well at the same time, but a robot can't? So then the question is, what do we need to do to replicate that?
Look to your left.
Skye has chosen motors that are powerful enough to swing the ropes, with an added feature.
The motor for the double Dutch machine is from a hoverboard. They're DC motors with encoders in them, so they can track the position.
The encoder setup uses magnetic poles mounted on the motor's shaft. A nearby sensor detects the changes in magnetic field as the motor spins, tracking the motor's rotational position and speed with precision. That information can then be sent to a computer to adjust the spin in real time. At least, in theory.
B, A and C were running right now. Not B. B isn't running, C.
For now, only 3 of Skye's 4 motors are spinning.
If these are 2 people's arms, it's just that it's like you step to the right. Okay.
They decide to align 2 working motors so they can work with 1 spinning rope for now.
Let's just turn it on. Let's just see. Yeah, this is slow enough where I could actually just walk into it.
It's an impressive milestone. The 2 arms turning the rope are perfectly in sync.
Okay, stop it. Okay. Oh my gosh, so good. I haven't seen anybody use it or anything this time.
Let's see. It's really important, especially in sort of engineering projects where there's a consumer, to sort of take prototypes and actually test them with your end users to see what their feedback is.
That's what I love so much about this project is Double Dutch is collaborative, and then robotics as an entire field, it combines 3 types of engineering: mechanical, electrical, and software engineering.
After making some tweaks to the code, they decide to try a true double Dutch jump.
You want to hear the pat, 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 pat. Okay, can you take it over from me?
With 2 of the working motors, Tahira guides Skye to be a stand-in turner.
Just snatch it from me. All right, all right. There you go. We'll just try with the little bit that's here.
With Skye's assistance, the motors are leading the way. And they're working like a charm.
Oh, that's so satisfying. Oh my gosh.
Okay. Thank you so much, Dr. Reed. This is amazing.
This was fun.
Working with Dr. Reed today was incredible. It was actually a dream for me. I felt like if I continue with this project, I'm gonna get there and then I'm gonna see myself as a different person who's capable of more than I used to think I was.
Meanwhile, after decades, Tahira is finally taking her own double Dutch design to the next level.
And when we've done small tests,
She's partnering with a product design company to turn her prototype into an affordable, consumer-ready version.
historically, what has been difficult has been how to design this system in such a way that it's fully functional and also cost-effective.
Which is why she still thinks that the most practical approach is to use only mechanical means to synchronize the motors. Tahira and Director of Industrial Design, Steve Escobar, are deep in the proof of concept stage. For now, they're working with a rudimentary plywood model to answer a few basic design questions.
Once you have an idea, how are you going to actually execute the idea? How are you going to design the idea so that people will actually want to use it? How are you going to make it accessible, both from a cost perspective, but also from a user interface perspective?
This first iteration of the design uses just one motor on each side, plus some good old-fashioned mechanical hardware, like gears, sprockets, and chains. Already, they're facing a few familiar challenges,
Looks like it's in sync, actually.
including getting the ropes in sync.
It's starting to go out of sync. Okay.
With years of double Dutch experience, Tahira knows exactly what the ropes should sound like.
We need to be able to hear a consistent pat, 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 but we're hearing. It's very rhythmic. That's why when stuff's out of beat, it's like the whole, this is just wrong.
If anything slips, it would be a tooth.
Using gears is a common sense way to keep the rotation of the ropes in sync, but something is wrong.
We think the weight of the rope is throwing this off.
When it's in motion, it's actually creating too much force for these arms.
Let's take some of these off and let's see what happens. Let's see, let me just listen for it.
How's it going?
Yeah, it's coming along.
Michael Sprov, president of Spec Design, stops in to see how things are progressing.
Where are we at, guys? How we
As a team, they talk about the day's testing and how to improve the design.
There's a lot to think about with some of the play that's still in the arms.
Your visit with Sky was very inspirational to us, and that was switching from a single motor with gears to 2 motors at each end. When you shared that with us, it really kind of turned the light bulb on.
It's extremely important to have different people who can see things from a different angle, because each one of us have our own blind spots.
Tahira's initial designs were rooted in her experience with mechanisms. But collaborating with Sky has expanded the possibilities for realizing the machine.
The best moments of ideation are, in my experience, collaborative, and they involve ideas bouncing off one another, being folded over, the negative of that idea being turned into the positive of this other idea.
Working together across different fields, what engineers call interdisciplinary collaboration can be a powerful multiplier. Though a lot more troubleshooting remains, Tahira's project is finally coming to life after decades of work.
Semi-surreal, exciting, it's a lot. It's heartwarming, it's... just glad. There's a message behind this product. When it gets on the market, there's a story to inspire young girls, young inventors, young minds, dreamers.
Tahira dreamt of a machine that could recreate the motions of another person's arms. But what happens when engineers take aim at a biological system that is far more complex, like vision, restoring the ability to see with an idea that once seemed like science fiction?
Landing rocket arm switch is on. Here comes the throttle.
Circuit breakers in. We have separation.
The $6 Million Man. I have to say, if there was any inspiration, that show was.
She's breaking up. She's breaking.
We can rebuild him. We have the technology.
When I was an undergraduate, I became interested in how electronics could be mated with the human body.
For more than 20 years, Phil Troik and his interdisciplinary research group have been pioneering a technology designed to restore some vision to those who have lost the ability to see. We've been using prosthetics to restore our body's abilities for thousands of years.
One of the most useful prosthetics has been the very humble glasses, right? So you have a sense of sight, but then there's a distortion in the curvature of your eye, so then you use a lens to compensate for that.
But this new device takes visual prosthetics to the next level.
The idea is to take the information you capture from a camera and bypass the eyes and optic nerve and go directly to the brain.
The state of neuroengineering is at its infancy with very, very promising avenues for growth. One that has been for a very long time a dream of engineers is to be able to interface with the nervous system.
Phil's group is the first to receive FDA permission to implant into the brain of a blind person a network of wireless stimulators, each just 5 millimeters across.
You see the electrodes sticking out there.
Even if they meet the criteria, the visual, the medical criteria, they have to be willing to embark on brain surgery. It's hard to find someone that fits into all of that criteria.
The team has qualified their first participant, Brian Bussard, who lost his vision completely several years ago.
Does the headband match my shoes?
It does, actually. That's perfect.
I was kidding.
Brian agreed to have a group of these stimulators surgically implanted in his visual cortex.
When you're considering designing something that will be implanted in a person, one of the safety checks is making sure that whatever that thing is, it doesn't actually harm a person.
And how did you sleep last night on a scale of 1 to 10?
For the trial, he is referred to as the participant, not the patient, as his collaboration with the entire team is essential.
I was going to be the first one. In my lifetime, I get to be the first of something that could change people's lives later on. You know, like who was the first person to walk on the moon?
One small step for man, one giant leap for mankind.
Artificial vision has really been enabled by advances in imaging technology. The development of incredibly tiny detectors and incredibly tiny communication signaling transmitters have enabled these implantable devices.
The implants in Brian's brain are receivers for signals that in turn stimulate the brain. The coil transmits signals that they hope the brain will interpret as visual information.
Each of those 25 arrays has 16 electrodes that we can stimulate on command. And the goal is to use those electrodes to activate the healthy neurons that are still there and just haven't been receiving normal visual input for a while.
What do I see? Probably the closest thing I would say is if you had blips on a radar screen.
The process requires creating a new kind of visual language.
Imagine getting these funny flashing lights from either a retinal or a cortical prosthesis that don't look anything like what vision used to be. And then your brain is beginning to discover there's a message to the madness. There is some pattern in here. And if I can try to find out how things hang together, then I can learn to understand what's around me.
People used to think, well, we need to recreate the signals from the eyes into that same neural code. But we've seen examples where if you establish an interface with those areas and you give them a consistent input, the brain will adapt and interpret those as best as it can.
As Brian continues to adapt, the work has progressed from the chair to a smaller cart-sized version of the system, connected by a cord, with researcher Michael Barry pushing the cart and following behind.
So we're putting on the visible light glass.
The basic idea is to capture images with a camera, technologically, somehow convert those images to the commands that go to each of these little modules.
Stand up slowly to your left.
The first real exciting thing for me was when we added a camera to it. And I went like this with my hand. And then I went like, oh, there's my thumb. So that was the first time in probably 6 years that I had a sensation of vision. That was exciting. It gave me a system.
So what we're going to work on today is a task of finding an open chair. Can you identify which chair is open?
Right there.
Great job.
Yeah, good job.
What we're providing is really a targeting system. It says, for whatever the camera is detecting, is something there. It says where something is, but you don't know what it is.
Let me find the cart. That way we don't pull the cords.
Hey, so do you want to try something infrared?
The team decides to expand the testing to include a camera that can see wavelengths of light beyond what humans can see.
Yep, so now we have the thermal sensor.
Why should you limit your wavelength to the visible range? Why not allow someone to see in the thermal range?
With his limited vision, infrared allows Brian to distinguish people and animals by their body heat.
For this task, you will find there's one occupied chair.
Oh, there's Grace right there. Hi, Grace. Nice to meet you. But you still have the big donut in the back of your head. You still have the wires for the camera. If you walk too fast, well, we can pull the coil. You lose signal, and you got to stop and reset.
There are a lot of technologies that work beautifully in the lab, right, where you have a lot of space, it's dedicated, and everything works well. But the reality is people move, they have their lives. They want to live the way they want to live and be mobile.
Nice to meet you.
With the basic technology working, the team has been building a system that condenses an entire cart of equipment into a wearable device, so Brian can go mobile. The camera records images that are translated by a mini computer into signals his brain can understand. These are then sent through a transmitter and beamed into Brian's implants, reaching his visual cortex.
Okay, so I'm gonna hook this on your belt, okay?
You should be good to go.
We're good to go.
You're freed up.
Trish was right there. She moved. Now she's right there.
I was just going to tell you can walk to me.
I was going to say, well, she's right there.
Yeah, I'm right here.
Okay, so I'm guessing this is tables over here? Or somebody, or something?
So as soon as he didn't have that starting and stopping of trying to keep the cart right behind him, yeah, he just decided to just walk around the room and see what all was here.
Becoming untethered was a big step. It gave me the flexibility to move and try and figure it out quicker or on my own. Okay, there's something here. Yeah, this is another table.
Yep, so now we have the thermal sensor.
There's somebody right there.
You found me.
Watching Brian see his wife without his eyes is a powerful validation of all their hard work.
The moment today when he had on the mobile unit and he walked to his wife and saw her, I just thought that was really a special moment.
She didn't make a sound, but you went to her, you found her in the room.
Do you think, oh my gosh, this man has lost his vision and now he can see something with the help of this engineering system strapped to him? All of these things have come together, all that iteration and testing and protocols.
The door.
It's pretty amazing.
This person is volunteering themselves, they're putting themselves at risk. They're doing so not because they expect to get vision back. It's for advancement of knowledge. It's for what we learn now will make possible what will become standard of care 100 years from now.
Somebody right there. Just from a human standpoint, I think we should be wired that we want to leave the world a better place than it was when we got here.
The following day, the team gathers to review their progress with the mobile system.
Did it accomplish the goal of making you feel more autonomous and liberated?
Well, full disclosure, if it would have been nice out yesterday, it would have been, oops, I made a left-hand turn and go out the door.
Now it's, okay, well, what do we prioritize next?
Probably the next step would be as if we can combine either the two cameras into one or even adding the second visual camera so we can get depth into it.
From an engineering perspective, engineering is not just a technology stemming from math and science. And the question we're asking is, how can an artificial interface like this be used to provide useful sensory information for someone who has blindness? We do have now the interface, albeit in somewhat simpler form than some would like, but we do have the interface and we are now answering the questions.
It's such a high-risk, high-payoff engineering challenge. Giving vision to someone who's visually impaired is just such a holy grail engineering strategy, and they've done it.
Our aspirations are high, and we only get there by making step-by-step incremental progress.
There he is. Hey, buddy.
I think we're proud of the fact that maybe we got there first.
Good boy.
I think we're done.
We're here today with the world around us as it is because we are hardwired to invent, design, and build tools. As we continue to boost our abilities with technology, it's anyone's guess what we'll create in the future.
When we go to create something new, we're stepping into the unknown.
With creativity and collaboration, we can solve even the most difficult problems.
Science fiction has always inspired the world, and it is the job of engineers to convert that inspiration into innovation and invent the solutions.
Building stuff to benefit all.